So, in the last class I have discussed about the design of an isolated footing resting on clay. Now, in that problem, so this is the isolated footing that I have designed in that problem. Now, if the foundation is the combined type of footing, then how we will design that. So, design procedure is same as this isolated footing. So, in that case you have to convert this all the weights that is coming for that foundation into that centroid of that foundation, and you choose the dimension according to that, and then check that dimension on the soil whether that dimension is safe against bearing capacity and settlement, and then you decide that which dimension you will choose. For example, suppose so this is the combined rectangular foundation. So, here the two columns load are coming W and W, this will be the one will be the W1, another will be the say W2. So, two the loadings are coming, and now we have to first I will discuss how I will choose a dimension of this foundation. So, this is the L is the distance between the two columns, x bar is the centroid distance from the center of this right or left column, and A1 and A2 are the distance from the center of the column to the edge of the right and the left portion of the footing. B is the width of the footing, L is the length of the footing. So, now the area is equal to will be W1 plus W2 plus W dash divided by the QS or Q safe. Okay. Q safe is the allowable bearing capacity against which I am designing it, okay. And the Q safe is the allowable or safe bearing capacity of the soil, and W A dash is the weight of the footing, which is generally taken as around 10% of W1 plus W2. So, this way I will get the area, this is the area I can get, and then suppose my dimension I am getting from that area is B cross L, okay. And then I can, if I take the moment of this loading from this this point, then I can write that W1 plus W2, because now here the W1 and W2 is acting, because here now I am assuming that this is acting in centroid. So, this is W1 plus W2, okay, because both the load now is acting in the centroid of this footing. So, W1 plus W2 into x bar will be equal to W2 into L, okay. L is the length of this distance between two columns. So, my x bar will be equal to W2 into L divided by W1 plus W2. Okay. Similarly, I can write that A1 plus x bar will be equal to here L by 2, or A2 plus L minus x bar, because A2 plus L minus x bar, that is also L by 2. So, now we have unknowns A1, A2, L, B, these are the unknowns. Okay. So, now how I can determine these unknowns, because now we have x1 x bar I can calculate, because L is known, W1 is known, W2 is known. So, I know the x bar. So, and I have this I can, if I assume any B value, L value, if I assume L value or B value, then if I know the area, then I can assume the B value. If I assume the B value, I can get the L value also, and then if I know the L value from here, I know if I know the L value, I know the x bar, I can calculate A 1 and A 2. So, based on that, I will take the dimension. Okay. So, now this dimension you have to now when we decide this dimension, then we have to go for the checking whether it is safe against settlement and bearing or not, and then we will do the design. So, same as the previous problem that I have solved. So, here the only thing is that you have to choose the proper dimension, what will be the B, L, A 1, A 2. So, this will be the so that the total load should act as the centroid of the footing, that is the case. And next one that I will do. So, this is the design of a raft foundation on clay. So, suppose we have a column arrangement is like this. Okay. So, this is the column arrangement of a building, and so this is the 3 meter center to center, each column has a say 3 meter center to center. So, 3 meter center to center this side, and this side also the each column is 3.5 meter center to center. This is also 3.5 meter center to center, this is also 3.5 meter center to center. Now, for this outer columns, each column is carrying 400 kilonewton, and the inner 4 columns they are carrying 600 kilonewton each. Okay. So, this outer columns are carrying 400 kilonewton each. So, now so first thing we have to check it whether the isolated footing is sufficient or not. Now, if we find the isolated footing is not sufficient and all the footings are overlapping each other, then in that case we will go for this raft foundation, where all the columns we are taking under one foundation. And another thing that we are in this case we are talking about the maximum settlement, but we have to also check if we are designing this isolated footing, that for the differential settlement also, because in different columns the loading is not same. So, your settlement will also be different. So, you check the settlement for every columns and then check whether that differential settlement is within the limit or not. If not within the limit, then you have to redesign the dimension of the footing such that total settlement as well as the differential settlement should be also within the permissible limit. Okay. But here we assume after the checking we find that this isolated footing is not sufficient. So, we are going for the raft foundation. So, we will take all the columns under a foundation, single foundation, and that is the raft foundation. So, what is the dimension for the first trial I am taking? So, the first trial I am taking. So, the B value is we are taking. So, this is the center to center, and then this is 1 to 3 into 3.5. So, that will give you distance between from this column to this column, center of this column, and then I am taking 1 meter this side additional plus 1 meter this side. Okay. So, that is the first trial I am taking, and because we have to provide some additional part from the edge of the footing for the edge of the column for the foundation. So, this is equal to 12.5 meter. Similarly, L also I am taking, this is 3 into 3.5, then I am taking the 1 meter in both the side additional from the center of the column. So, 1 meter plus 1 meter, that is also 12.5 meter. Okay. So, this is the dimension. Now, what is the total load is coming on this foundation? So, total load is coming, there are outer column is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, 12 columns they are taking 400 kilonewton load and 4 columns are taking 600 kilonewton load. So, the total load is 7200 kilonewton. Okay? And the dimension is taken 12.5 cross 12.5. And so, the net load or stress that is acting on the base of the foundation is 7200 divided by 12.5 into 12.5. So, that is equal to 46.1 kilonewton per meter square. Okay? And we have assumed the depth of foundation is at 1.5 meter below the ground level. So, this is the assumption for the first trial. Now, come back to the soil properties. Okay? So, this is the base of the foundation where the net stress that is acting is 46.1 kilonewton per meter square and the width is taken as 12.5 meter. Okay? And this base of the foundation is at 1.5 meter below the ground level, and ground level say here. So, this is GL, this distance is 1.5 meter and this is plus 0 meter, and water table is also at a depth of 1.5 meter. So, this is the water table location. So, this is also water table location which is 1.5 meter below ground level. So, now the soil has 4 layers. This is the first layer, second layer, third layer and the fourth layer. After that is a rigid bed, and as I mentioned, for the rigid bed there will be no settlement. So, this is the rigid bed or the rock bed. So, now the dimension is given. So, this layer is minus 4 meter, this is minus 12 meter and this was minus 20 meter and this is minus 30 meter. Okay. So, the properties that are given, this is layer number 1, layer number 2, layer number 3 and layer number 4. Okay. And the properties that is given for the first layer, this is kilonewton per meter cube unit weight and Cu is 60 kilonewton per meter square and Cc 1 plus E 0 is equal to 0.05 and E value is equal to 42,000 kilonewton per meter square. So, again if the E value is not given, so for a normally consolidated soil the reasonable 700 to 1000 in between or 750 and 700 Cu will be a reasonable value. So, that I have used in the previous problems. So, again for the second layer unit weight is 18 kilonewton per meter cube and your Cu value is 25 kilonewton meter square. Cc 1 plus E 0 is 0.1 and E is taken to 4500 kilonewton per meter square. For the third layer, unit weight is 19 kilonewton per meter cube and Cu value is 70 kilonewton meter square and E value is given 49000 kilonewton per meter square and Cc 1 plus E 0 is equal to 0.06. Okay. And for the fourth layer, unit weight is 19 kilonewton per meter cube, Cu value is equal to 100 kilonewton per meter square and E value is 70,000 kilonewton per meter square and Cc 1 plus E 0 is 0.03. Okay, so, these are the values are given and we have to now design the foundation. And remember that here if you find that for the bearing capacity calculation our influence zone is B and B is 12.5. So, 12.5 this is 1.5. So, and below here 12.5 will be somewhere here. So, that means the most of the layer is influence is the second layer. Okay, and the minimum lowest Cu value under equation is 25 and that is for the second layer. So, one thing that as the most of the layer is influenced by the second layer, because this layer thickness is say 2.5 meter, this layer thickness is 8 meter, this layer also 8 meter, this layer is 10 meter. But the influence zone, because this is 12.5. So, 10.5 and 2 meter. So, this layer the third layer is influenced by only up to 2 meter. So, the third layer is influenced by up to 2 meter, then the first layer is influenced by 2.5 meter. So, and the second layer is influenced by 8 meter. So, that is the maximum. So, one way that you can take the lowest value of Cu and you can do the calculation, because that will give you the the safest design. Okay. So, because you are taking the lowest Cu value, but I would prefer to take the weighted average, but if you want you can take the 25 also, because that is the lowest value and the most, and that influence zone is covered by the second layer only, most of the influence zone is covered by second layer and that is giving the lowest value. So, you can take that value as your design Cu, but I will prefer to take the weighted average. So, that is why I will take the weighted average of Cu. So, yeah. So, that means now the first checking is the bearing capacity, and again this is for the C soil only, Cu soil only. So, I will take net ultimate is Cu Nc and I will take the Skempton expression that I have used for the isolated footing also. So, Nc value in general way for the rectangular footing is 5 1 plus 0.2 B by L into 1 plus 0.2 df by B, and for the square footing this will be 6 1 plus 0.2 df by B, that is for square foundation as B by L is equal to 1. And so, this value is coming out to be 6 1 plus 0.2, df is taken 1.5 meter, B is 12.5 meter. So, this is 6.14 and this is not greater than equal to 9. So, I can take 6.14 as a value, because it cannot be greater than 9 also as per the Skempton recommendation. So, I am taking the CU average is equal to, so for the first layer the 2.5 meter is influence zone, and that is CU value is 60, because in the first layer CU value is 60 and 2.5, second layer 50 is the CU value, influence zone is 8 meter, and the third layer influence zone is again 2 meter and CU value is 70. So, then plus 25 into 8 plus 2 into 70 divided by 12.5 meter, and that is equal to 45.6 kilonewton per meter square. So, Q net ultimate is 45.6 into 6.14 or 6.144, that is equal to 215 kilonewton per meter square. Okay. So, my factor of safety is equal to 215 divided by net stress that is acting, which is 46.1, because net stress is 46.1 is the net stress, and then that is equal to 4.7, which is greater than 2.5 and safe. So, it is very much safe, I can say, because 2.5 is requirement, 2.5 to 3, it is 4.7 close to 5. So, but let us see whether how much it is safe against settlement, then we will decide whether we will redesign it or not. Okay. So, the next one we will do the settlement calculation, and for the B is the settlement calculation. And first we will do the immediate settlement calculation. So, our Q net is equal to 46.1 kilonewton per meter square, B is equal to 12.5 meter, and mu value as it is clay will take 0.5, and the again E average or weighted average I am taking. So, here now the influence zone is 2.5 in 12.5 into 2, that means 25 meter is the influence zone, but my thickness of the layer before it is before the rigid bed is 2.5 plus 8 plus 8 plus 10. So, it will be your 16. So, that the total thickness will be 2.5 plus 8 plus 8 then plus 10. So, that means it is equal to your 28.5 meter. Okay. So, this is 28.5 meter, but my influence zone is 25 meter. So, the total fourth layer is not within the influence zone, but some part of the fourth layer is within the influence zone. So, now this is 28.5, but actual influence zone is 25 meter. Okay. So, now the E average I am taking is, this is 42,000 into 10 to the power 3, that is for the first layer. So, first layer thickness is 2.5 meter and this is 42,000. So, first layer 42,000 and 2.5 meter. For the second layer it is 24.5 into 10 to the power 3 kilonewton per meter square. So, it is 24,500. So, and thickness is 8 meter. So, I can write this is 24.5 into 10 to the power 3 and thickness is 8 meter. Similarly, for the third layer it is 49,000 into 3 and the thickness is 8 meter, but for the fourth layer the thickness will be only 6.5 meter. Okay. It is not the total one. So, for the next layer is 70,000 is the E value kilonewton per meter square. So, it will be 6.5 meter. So, total thickness 8816 and 18.5 plus 6.5. So, it will be 25 meter, okay, because that is the influence zone. So, my E value is 46000 kilonewton per meter square. So, the SC or the rho C, that means the rho I is the immediate settlement, and that is Qn B by E into 1 minus mu square into IF. So, that is equal to 46.1 into 12.5 divided the E value is 46,000 and 1 minus 0.5 square, and again it is a square foundation. So, at the center is 1.12 is the IF value from the table. So, IF is 1.12 from the, and remember that here IF I am taking the flexible foundation center for the square footing, and later on we will apply the rigidity correction because it is a rigid foundation. So, that is why we can take the flexible foundation IF value at the center, that is taken here. So, this value is 10.52 millimeter. Now, the corrections, the first correction is the rigidity correction, which is equal to 0.8 because it is a rigid foundation, rough foundation, and second correction or correction factor, this is the depth correction factor, your the value is d by root over L b. So, the d is 1.5 meter, then root over 12.5 meter, then cross 12.5 meter. So, this value is 0.12 and corresponding L by b is equal to 1, and this value is factor is equal to 0.98 from the, this is from the chart or Fox chart. Okay. So, from the Fox chart I am getting the rigidity correction, depth correction is 0.98. So, SI corrected will be equal to 10.52 into 0.8 into 0.98. So, that is equal to 8.2 meter. Okay. So, the immediate settlement that I have calculated is 8.2 millimeter, and now I have to calculate the consolidation settlement, then we will see whether the dimension that I have chosen is within the permissible limit or not. So, in the next class I will calculate the consolidation settlement, then we will finish this problem. Thank you.